It was 1928. The brilliant and famously introvert physicist Paul Dirac was facing an intellectual crisis. He set out to achieve one of the great goals of modern physics, to write a single equation that could describe an electron while obeying the laws of both quantum mechanics and Einstein's special relativity. After a colossal effort, he was successful. The result, known today as Dirac equation, was masterpiece of mathematical physics. It was beautiful, it was powerful, it was elegant, but it held a dark secret, a ghost in the mathematics that seemed to defy reality. Let's start with where physics was in 1926. Erwin Schrödinger had given us his famous wave equations, one that describes how quantum particles behave. It was revolutionary. For the first time, we could predict how electrons move around atoms, how they form chemical bonds, and it worked beautifully. Here it is in the simplest form. But there was a problem. This equation was not relativistic. It doesn't account for Einstein's theory of special relativity. And that matters because when particles are zipping around fast, relativity becomes very important. To understand the problem, let's compare two equations. In classical physics and in Schrödinger's equations, this works great in everyday speeds. But Einstein showed us something different. In his theory of special relativity, notice the square on the energy? That's the problem, especially for heavy atoms where electrons zip around very fast. So in 1928, Paul Dirac asked himself, can I write down a wave equation that respects Einstein's relativity? If you want to use this equation in quantum mechanics, you need to take the square root. But square roots are messy. They give you plus or minus. And that creates all sorts of mathematical problems. His equation was remarkable because first, it's linear in both time and space derivative, no messy square roots. Second, it is completely consistent with Einstein's special relativity. When you look at the particles moving slowly compared to light, it reduces right back to Schrödinger's equations. But then something strange also showed up in the solutions. Let's visualize the energy states. Here is the zero energy in the middle. Einstein's relation tells us that a particle at rest has energy equals to its mass times c squared. That's the famous E equals to mc squared. So the positive energy states starting at plus mc squared and going up. Now that makes sense. They describe normal particles like electrons. But here's the weird part. The mathematics also predicts negative energy states starting at minus mc squared and going down. Now negative energy is something very difficult to wrap our head around. It's like a ball, instead of rolling downwards, it's rolling uphill. That's negative energy. And any particle with negative energy wasn't just strange, it threatened to break the universe. It implied that all electrons should spiral down into infinite abyss of negative energy, releasing endless radiation. It meant the matter could not be stable. Since the world is obviously stable, the equation seemed to be a catastrophic failure. Dirac was so troubled by this that he nearly abandoned his own masterpiece. And then he came up with an interpretation that seemed crazy, but turned out to be absolutely correct. He said, what if all energy states are already filled? Imagine infinite sea of negative energy particles filling all of space. We call this as the Dirac sea. Normally, we don't notice the sea. It's just in the background, the vacuum. What if we could knock one of these particles out of the sea, creating a hole? This hole would behave very strangely. It would appear to have positive energy because removing negative energy is like adding positive energy. And if the particle we removed had negative charge, the hole would appear to have positive charge. Dirac realized the hole would look exactly like a particle but with opposite charge. He had predicted antimatter. Specifically, his equation predicted something called as anti-electron, a particle with same mass as an electron but with positive charge instead of negative. A quantum rule called Pauli's exclusion principle prevents the positive energy electrons from falling in, simply because all the negative spots are already taken. This neatly explained why matter is stable. Then he took it one breathtaking step further. What if, he wondered, a high energy photon strikes this invisible sea and knocks one of the negative energy electrons out, giving it positive energy? That electron would pop into existence in our world. But it would also leave behind a hole in the sea. And this hole, Dirac reasoned, would behave just like a particle. It would have the exact same mass as an electron, but because it's a hole where a negative charge used to be, it would have opposite charge, a positive charge. He had just predicted an anti-electron, a perfect mirror image twin of the electron. In 1928, it was the birth of the concept of antimatter. But there was no proof of it. It was just a mathematical solution, a ghost in mathematics. An idea so strange that most physicists were deeply skeptical. It sounded more like science fiction than serious physics. The world would need proof, and that proof would not come from a theorist's blackboard, but from a mountain top in California. Enter Carl D. Anderson. In the early 1930s, Anderson was a young, ambitious physicist at Caltech. He wasn't looking for antimatter, he was even barely aware of Dirac's theory. His focus was on something far more tangible, but just as mysterious: cosmic rays. Cosmic rays aren't rays, but a constant shower of high energy particles raining down on Earth from deep space. As messengers from cataclysmic events like supernova, they are supercharged with far more energy than any lab on Earth could produce. For physicists like Anderson and his mentor Robert Millikan, these particles were free ticket to exploring the fundamental nature of matter. To see these cosmic messengers, Anderson built a clever device called cloud chamber, a sealed container filled with supersaturated vapor. When a charged particle zips through it, it leaves a trail of ions, and the vapor condenses around them, forming a delicate misty line, a visible footprint of the invisible particle. Anderson's setup had a few crucial tricks. He placed the entire chamber inside a massive electromagnet, which would cause the charged particle to curve, negative ions bending one way and positive ones the opposite. The sharpness of the curve also revealed the particle's momentum. Then he added the most important part: a thick 6 mm lead plate right in the middle of the chamber. Its job was simple: to slow the particles down. By comparing the curve of the track before and after it hit the plate, Anderson could know for sure which direction the particle was moving. This simple piece of lead was about to become a silent witness to a historic discovery. On 2nd August 1932, while sifting through the latest batch of images from his cloud chamber, Carl Anderson saw something that made him freeze. Most photographs showed the familiar signature of the universe: the thin, graceful curves of lightweight negative electrons and the thick, straighter tracks of heavy positive protons. There was one photograph that showed something wrong. The track was thin, just like an electron's, meaning that it was a lightweight particle, but it was curving the wrong way, in the direction of positive charge. The immediate guess was a proton, but it didn't fit. You see, a heavy proton would have punched right through the magnetic field with almost no curve. This track curved exactly like a particle with a mass of an electron should. He was looking at a particle that behaved like an electron but had a positive charge. The simplest explanation was that it was just a regular electron traveling upward in the opposite direction through the chamber. An upward moving negative particle would curve in the same way as a downward moving positive one. It was plausible, boring explanation that would have explained the anomaly away. But this is where Anderson's clever lead plate became the hero of the story. He looked closer. The particle had passed right through the lead. He measured the curvature of the track above and below the plate and found the smoking gun. The track was more curved after it passed through the plate. This meant it had lost energy smashing through the lead, causing the path to bend even more sharply. This proof was irrefutable. The particle was moving downward. The conclusion was inescapable. It wasn't an upward moving electron, it was a downward moving particle with a positive charge and a mass identical to that of an electron. He first called it a positive electron, a name later shortened to positron. Without even trying, Carl Anderson accidentally taken the first picture of antimatter. The mathematical ghost that haunted Dirac's equation was real. Anderson published a short, cautious paper about his finding in September 1932. The scientific community reacted with a mix of excitement and skepticism. A claim this large, based on a single photograph, could easily be a fluke. More proof was needed. And that proof came quickly from Cambridge University, where physicist Patrick Blackett and Giuseppe Occhialini were studying cosmic rays with even more advanced and automated cloud chamber. When they heard of Anderson's result, they re-examined their own photographs. They had seen similar strange tracks before, but had dismissed them as anomalies. Now, knowing what to look for, they found them everywhere. In early 1933, they published a paper confirming Anderson's discovery beyond all doubt. But they found something even more incredible. Their photos showed showers, multiple tracks originating from a single point. In these showers, they saw it, a high-energy gamma ray, a particle of light, would hit a lead plate and spontaneously create a pair of particles that flew off in opposite direction. One was electron and the other one was positron. This was a pair production, a stunning confirmation of Dirac's theory. Pure energy was being converted into matter and antimatter, perfectly following Einstein's E equals to mc square. If an electron and a positron meet, they would destroy each other, disappearing in a flash of pure energy. The evidence was overwhelming. For his accidental discovery, Carl Anderson was awarded the Nobel Prize in Physics in 1936. The discovery of positron didn't add a new particle to the zoo. It revealed that a secret mirror image world was woven into the very fabric of reality. It kicked off a whole new field of physics. If you love these stories of accidental breakthroughs that changed our world, take a moment and hit that subscribe button so you don't miss our next adventure. The confirmation of antimatter was turning point. It established a wild new rule for the universe. Most fundamental particles have antiparticle twin with same mass but opposite charge. Soon, the antiproton was discovered, and antimatter became the core part of standard model of particle physics. While entire galaxies made of antimatter remains science fiction, the positron itself has found an amazing life-saving job right here on Earth, the PET scan or positron emission tomography. Here is how it works. A patient is given sugar-like molecule tagged with a substance that emits positrons. Because the cancer cells are highly active, they gobble up more of this sugar than healthy cells. As the tracer decays inside the body, it releases positrons. These positrons only travel a millimeter or two before they inevitably run into an electron. The moment they meet, they annihilate each other. They vanish, and in their place, two high-energy gamma rays shoots off in almost exactly opposite direction. The PET scanner is a ring of detectors that captures these pairs of photons. By tracing these lines from where the photons hit, a computer can pinpoint the exact location of the annihilation. Mapping millions of these events, build a 3D image showing where the tracer has accumulated. This incredible tool allows doctor to see the metabolic activity in the body, to check tumor growth, to check if the therapy is working, or study the blood flow in the heart and brain. It allows us to watch the chemical processes of life and disease in real time. And it all started with Carl Anderson's single impossible photograph. The journey from a strange mathematical solution to a life-saving medical tool shows the power of pure curiosity. Dirac wasn't trying to solve a puzzle with his equation to cure disease, and Anderson wasn't looking for a new type of matter, but their refusal to dismiss an anomaly ended up changing our view of reality itself. And yet, that discovery has left us with one of the biggest unanswered questions in physics. The Big Bang should have created equal amount of matter and antimatter, which would have annihilated each other, leaving a universe of pure light. But instead, we live in a cosmos of matter. So where did all the antimatter go? The story that began with a ghost in an equation and an impossible track on a photograph is far from over. It's a powerful reminder that sometimes the deepest truths are found not when you're looking for them, but when you have the courage to investigate a single impossible clue. Thanks for watching.